Regression. In a classification, given an input, the output that is generated is Boolean. It is a yes/no answer. When the output is a numeric value, what we would like to learn is not a class C of x, which is chosen among 0 or 1, but a numerical function. In machine learning, the function is not known, but we have a training set of examples drawn from it. That is, x equals to such kind of tuple, the set of x to the t and r to the t, where t starting from 1 to n, where r to the t is in R, defined in a real number. If there is no noise, the task is interpolation. We would like to find the function f of x that passes through these points such that we have r to the t equals to f of x to the t in polynomial interpolation. Given n points, we find the n-1st degree polynomial that we can use to predict the output for any x. This is called the extrapolation if x is outside of the range of x to the t in the training set. In time series prediction, for example, we have data up to the present and we want to predict the value for the future. In regression, there is noise added to the output of the unknown function r to the t equals to f of x to the t plus epsilon, where f of x is in R, is the unknown function, and epsilon is random noise. The explanation for noise is that there are extra hidden variables that we cannot observe, that r to the t equals to f star of x to the t z to the t, where z to the t denote those hidden variables. We would like to approximate the output by our model g of x. The empirical error on the training set x is expectations of g conditioning on x equals to 1 over n, this is the average, times the summations of the following n variables, where index t starting from 1 to n, these n indexes, and the tenor to be summed is r to the t minus g of x to the t. Such a difference then we take to the square. Because r and g of x are numerical quantities, for example, they are in real number, there is an ordering defined on their values, and we can define a distance between values as the square of the difference, which gives us more information that equal or non-equal as used in classification. The square of the difference is one error function, or called loss function, that can be used. Another is the absolute value of the difference. We will see other examples in the coming chapters. Our aim is to find a g dot that minimizes the empirical error. Again, our approach is the same. We assume a hypothesis class for g dot with a small set of parameters. If we assume that g of x is linear, we have g of x equals to w1 x1 plus w2 x2 and so on plus wd xd plus w0, which is equals to the summations of wj xj, summing with j starting from 1 to d, then plus w0. Let us now go back to our example in section 1.2.3, where we estimated the price of a used car. There, we used a single input linear model, g of x equals to w1x plus w0, where w1 and w0 are the parameters to learn from data. The w1 and w0 values should minimize the expectations of w1 w0 pair conditioning on x, which is equals to, by the formula, again, 1 over n times the summations, summing for all index t starting from 1 to n of the following terms. The square of the difference between the following two terms. The first is r to the t. The second is w1 times x to the t plus w0. So its a minimum point can be calculated by taking the partial derivatives of e with respect to w1 and w0, setting them equal to 0, and solving for the two unknowns. What are those two unknowns, w1 and w0? They are formulas. w1 is equal to the summations of x to the t times r to the t minus x times xr bar times n, where this summations is summing for all possible t. And in denominator of W1 is the following formula. Again, the summations for all t with the following terms: x to the t to the square minus n times x bar to the square, where this bar means the average numbers. Okay, then what is W0? Again, this is the formula. That is R bar minus W1 times X bar. Where X bar is equals to the summations of X to the T divided by N, where the T is the summing for all, where the summation is summing for all T, and R bar is the summations of all R to the T, then divided by N. The line found is shown in figure 1.2. If the linear model is too simple, it is too constrained and incurs a large approximation error, and in such a case, the output may be taken as a higher order function of the input, for example, quadratic. G of x equals to W2 times x to the square plus W1 times x plus W0, where similarly we have an analytical solution for the parameters. When the order of the polynomial is increased, the error on the training data decreases, but a high-order polynomial follows individual examples closely. Instead of capturing the general trend, see the sixth-order polynomial in figure 2.10. This implies that O'Kane's razor also applies in the case of regression, and we should be careful when fine-tuning the model complexity to match it with the complexity of the function underlying the data.